In this video, we're going to discuss parametrized families of differential equations, and along with that we will discuss bifurcations. I'll explain what all this means. So I'm going to use as an example a model that we've already looked at. Suppose that we have a bucket of water. It contains 5 gallons of water in it, and what we're going to do is we're going to input every minute 1/4 pound of salt along with a 1/2 gallon of water into the bucket, and there's a spigot at the bottom that will take out 1/2 gallon per minute of the water that's inside the bucket. The same amount of water is going in as is going out, and so therefore this will stay at 5 gallons of water, but what will change is how much salt is in there. So if we let S be the amount of salt in the bucket, we come up with a differential equation that looks like this, and we've done this problem, or you've done this problem already, and you can review how this differential equation comes out of that situation, but there it is. So that is all well and good, but in mathematics what we like to do is not reinvent the wheel every time we see a similar problem. So we often replace concrete numbers with letters, with stand-in parameters or variables, and in that way we sort of are solving a whole bunch of problems all at once. So what I'm talking about in this case could be something like this. We could, instead of committing to 1/4 pounds of salt per minute, we could replace that with a letter, A pounds per minute of salt. Okay, and that's called a parameter. It's a letter, so you might call it a variable, but that's maybe not the best word, because for any one given problem, A wouldn't be varying, it would be a specific number, like it's 1/4 here. So it's not a variable in the problem, but from one version of the problem to the next version of the problem, it could change. And then we call that a parameter. So in this case, we're replacing the one number with a parameter A. Now if you do that, the differential equation, of course, is almost the same, except that that 1/4 gets replaced by an A. And analyzing this differential equation now is basically analyzing all these situations all at once for any value of A. And so this is called a parametrized family. Of differential equations. Essentially, we have this whole family of differential equations where A could be anything. I guess technically for this real-world problem, A should be a positive number. But, you know, we can, although it wouldn't make physical sense, we could just look at this differential equation for its own sake and allow A to be 0, allow A to be negative, just to see what happens. Yeah. Now, in this case, this is a one-parameter family, right? There's only one of these non-specified parameters. You can have 2-parameter families or 3-parameter families. Okay. Now, what can you do and what can't you do with a parametrized family? Well, one thing you can't do is Euler's method. Euler's method really requires concrete specific numbers, because you're grinding out specific numbers. So you can't have an A in there, or literally everything in your table would depend on that A, and it would be a big mess very quickly. So we can't do Euler's method. Depending on your software, you may or may not be able to do slope fields. Really, you can't do slope fields because, again, the actual picture would depend on what A is, so you really sort of need to specify an A to get an actual slope field. I say depending on your software because some of the TI Nspire calculators, the TI Nspire CASs, allow you to put a parameter in for your differential equation and then put a slider so that you can sort of let A like sort of range from, say, 0 up to 5 or something like that, and you can move this slider and see how the slope field changes. So that's very useful. Of course, at any one moment you are seeing only one of the slope fields for a particular value of A. Okay. You can solve it analytically using whatever method might work. So for example, separation of variables is the one method we know so far. And you can, this guy is just like the original one, this guy is autonomous, so it is separable. And you could solve it, and you would just have an A in your answer. So that's something you can do with a whole family, a whole parametrized family of differential equations. And you can sort of do phase diagrams as well. And that's what I want to focus on right now. Okay. Okay, so we take the differential equation. We want to do a phase line. Here's our phase line set up, and I know we don't usually put such a specific scale on here. We sort of do it after the fact, after we've put in the equilibrium points. But I'm going to put on this scale going by ones on our phase line. Okay, so, you know, of course, if I just temporarily go back to the original one where A was 1/4, we know how to find the equilibrium. We set it equal to 0, so we get 1/4 equals 1/10 s. Multiply by 10, you end up getting s equals 5/2, or 2.5. Right. So there's the equilibrium point, and then we test a point below, test a point above. If we plug in 0 right here, we get a positive answer, so we know it's going up. And if we put in a bigger number like 3 or 4, you'll see that you get a negative number, so it's going down. So there in blue is the phase line on this black axis. Okay, that's all well and good. Now, that was just for a specific A. So let me in fact label this as A equals 1/4. That's the A equals 1/4 phase line. Okay, now of course we could change it. Let's do 1/2. All right, so we set that equal to 0. We get 1/2 equals 1/10 s. You can see that s will be 5. So we make a new phase line, and the equilibrium is at 5. And again, if you check the upper part and lower part, we get the upper part again is pointing downward, the lower part is pointing upward. So the equilibrium has shifted upward. Okay, and you can do this for various numbers plugged in for A, but of course the whole point of this is we want to do it all at once. So if I do A minus 1/10 s equals 0, I get s equals 10a. So now I've figured it out for all of them all at once, or at least the equilibrium position. You can also tell, I think, that if you put in a number bigger than that here, you'll get a negative number, and if you put in a number smaller than that for s, you'll get a positive number. So again, the arrow for the upper part will be going down, and the arrow for the lower part will be going up. So now we can quickly do the phase line for, say, 3/4. When we plug in 3/4 for A, we've already got the answer. It'll be 7.5. It'll be up there. Again, it'll be down and up. All right, so, and you can see that what's kind of going on is that the equilibrium numbers are kind of forming a straight line, right? In fact, given by the formula 10a, that's linear in terms of A. We could also go the other way, do A equals 0, for example, then we see that the equilibrium solution is at 0, which is the extension of this, pretty much. And again, it would be a downward here and an upward on the other side. Okay, and I could go further. If I went further to the right, I'd be off my phase line. I'd have to extend my phase line a little bit higher. But you get the point. It's like for each value of A, I just did a little sample of 4 of them. I get a phase line, and we can kind of link them up, and we can see how the phase line changes, how the equilibrium changes, and the arrows change. The arrows aren't changing. The arrows, their sections are shifting upward along with the equilibrium shifting upward, right? Okay. So this sort of creates a diagram that shows you the whole situation, allowing you to see what's happening as you change A. So that's a good way to analyze a one-parameter family of differential equations. Now consider this example. dy dt equals y squared minus ky plus 1. So there's our parameter k. Again, in any specific situation, k would be a number, but we're trying to do sort of all possibilities for k all at once. So we have this family, this parametrized family. Okay, so let's just do it right from the start with k as our parameter. Let's not plug in any specific numbers. So the whole point is to save time by leaving it as k. So we're going to do a phase line. We first find the equilibrium solutions. We see that we've got a quadratic here, so we would use the quadratic formula. 2a on the bottom. On the top would be negative b, so positive k plus or minus the square root of b squared, so k squared, minus 4ac, so minus 4. And with a quadratic, we have to be careful to interpret this. With a quadratic, the square root part, the part under the square root, could be positive or 0 or negative. That's called the discriminant often. And if the discriminant is negative, we actually don't have a solution, at least not a real number solution, right? So k squared minus 4 would need to be either 0 or positive for us to really get equilibrium solutions. Okay, so what does that all imply then? Here we go. We're going to do a series of phase lines for a specific k, k being 0, 1, 2, 3, 4, and 5 as an example. But as we just noted, if k is less than 2, we know that this doesn't exist. We don't get any solutions. So for the 0 and the 1 phase line, we have no equilibrium points. We have no equilibrium points. So no dots to put on here. So each phase line is just really one big section. And so it'll just get one single arrow. Now, let's see. For example, when k is 0, this would be y squared plus 1. I can see that no matter what I plug in, I will always get a positive answer. In fact, it'll always be 1. So this will just be a upward arrow. And for k equals 1, I'll have y squared minus y plus 1. And again, I think if you check, if you plug in any number, you'll see you always get a positive number. It never goes negative. Okay, so again, just it's kind of a boring phase line, just up all the time. Any solutions would just grow. They would just go up. Okay. But then when we get to k equals 2, we do get equilibrium solutions back here, right? So when k equals 2, this will be 0, so I'll just get 2 over 2. I just get 1. So I get an equilibrium solution right there. And now I have two sides to check. So let me see, y squared minus 2y plus 1. So actually, I happen to notice that that actually factors as y minus 1 squared. So other than the fact that when I plug in 1 I get 0, which is kind of obvious now, I also see that if I plug in anything else I get a positive number, so because of the square, right? So on this side it's up, and on this side it's up. But we have this one equilibrium solution. By the way, that equilibrium solution right there, therefore, is what we would call a node, right? It's neither a source nor a sink, it's a node. Okay. Now what happens at k equals 3? So at k equals 3, we get a 9 minus 4 here. We actually get a square root of 5. So we get 3 plus square root of 5 over 2, and we get 3 minus square root of 5 over 2. So we're actually getting two answers now. Now if you put them into your calculator, you'll see that you get 2.618 for the plus 1 and 0.382 for the minus 1. So it's going to be sort of one will be like right here, and one will be like right here. And again, if just to speed this up, if you check things, you will get an upward arrow here, an upward arrow down here, and in between you get a downward arrow. So this is really neat. Apparently you get truly different behavior. It's not just slightly nudging things and making them like just move over a little bit, like in our first example. The value of k actually changes the possible behaviors that you can get out of this differential equation. When k is down at 0 or 1, or even 2, all or almost all solutions increase, they go up. But when k equals 3, we see that there's a range of initial conditions. If you start in here, you will actually go down. That's new behavior that's popping out for this value of k. Now we can continue. If k equals 4, again, we'll also get two answers. In decimal form, if you plug them into your calculator, they end up being 3.732 and 0.267. So I think right here and right here. And again, up, down, up. You can check that for yourself. And then one more, 5. Again, two answers. You get 4.791 and 0.209. So almost the same points, just slightly lower here. And now here we're almost up at 5. We're like here. Okay. And again, up, down, up. And if I do what I did before, I can connect the equilibria It goes like that. A little more curved here. Sorry, it's hard to control the mouse here, but it kind of goes like that. I didn't mean for this to be a straight line. It is definitely not. Okay. Yeah. And so that is what we get. And in fact, what you get here is a graph of this as a function. The top part being if you took the plus, and the bottom half of the curve being if you took the minus. So really two different functions, two different graphs, and they're meeting right here. Okay. But this is really cool, and this is something we want to notice when it comes up in a parametrized family. A difference in behavior between these guys and these guys. So for k bigger than 2, we actually have 2 equilibrium solutions, and sort of other than those we have 3 basic different kinds of behavior: an up, a down, and an up. And then k equals 2 itself is actually exactly the dividing point. So I should have extended this all the way to here, right? So like if we had done k equals 1.9, it would have been like the first two. K equals 2 itself is a special case. It's exactly the dividing line between these two kinds of behaviors. It's got one equilibrium point, and on either side it's up. So you can sort of see this evolution of the phase line as k changes. And 2, of course, is the key parameter value. And so this is what's called a bifurcation. So a bifurcation is when an equilibrium sort of comes into being as you change a parameter and then splits into 2 or more. The bi sort of is biased toward splitting into 2 like we have here, but you can sometimes get 3 and different numbers. We still just call it a bifurcation. Basically, a bifurcation is when you have different behavior, truly different qualitative behavior for different values of the parameter. And that is a very interesting thing to notice.